So, here we are at the last planning algorithm that we will study. It is quite a well known algorithm called algorithm Graphplan. It was devised or presented to us in 1995 by Blum and First, and it takes a very different view of the planning problems from the ones that we have taken so far. So, what are the views approaches we have said? We have said there is state space planning or there is plan space planning. Blum and First gave us a different approach we will study now essentially. So, instead of searching for a solution either in the state space or in the plan space, it first constructs an intermediate structure which is called a planning graph that potentially captures all possible solutions, and then it proceeds to search for a solution in the planning graph. So, it is a two-stage process. So, the idea that Blum and First gave us was that of a two-stage process, that in the first stage you construct a structure, in this example it is a planning graph that we will see, and in the second stage you search inside that structure, inside the planning graph. So, starting with Graphplan, a variety of new planning algorithms came forward in the 90s essentially, and they are important to us because these algorithms, they increase the length of plans that could be constructed by an order of magnitude. So, initially if the planning algorithms that we have studied so far could construct plans of length 10 or 15 or 20, now they could construct plans of length 100 or 200 essentially. So, obviously they are more effective in that sense, and the process that they all employ, these new algorithms, is two-stage planning. So, Graphplan pioneered this approach of two-stage planning, construct a planning graph and search for a solution in this planning graph. Another planner that came around that time, and you can see that this is in fact presented even before Graphplan, is that of SAT plan by Courts and Selman and McAllister. What they say is convert the planning problem to a satisfiability problem and use an off the shelf solver to solve the SAT problem. So, we have already seen the SAT problem, and what this approach says is that convert the planning problem to a SAT problem, and then of course, somebody must have developed a solver for SAT. So, we can use that. That is in the general way that we want to approach AI, that we want to write general solvers and then pose problems to fit into those general solvers. There was another planner called C plan, which is based on constraints by Van Beek and Shen, 1999. What they do is convert the planning problem to a constraint satisfaction problem, and then which is a CSP, and then they use again an off the shelf solver to solve the CSP. We will look at CSPs later in this course and how to pose problems in CSP and how to solve them. So, another direction that came along the same time was this heuristic search planners. This is for the sake of history that I am mentioning it here. And what they did was they used something called domain independent heuristics to guide state space search essentially. So, these were state space planners, but they were using what is called as domain independent heuristics. We will not have a time to look at this, but we had briefly mentioned it when we were looking at heuristic search, that for example, in the 8 puzzle we mentioned that the Manhattan distance heuristic could be thought of solving a different problem in which a tile could slide over another tile. And then essentially the idea of domain independent heuristics is that you relax the problem in such a way that its solution can be found in polynomial time, then solve the relaxed problem, which will give you an estimate of which of your successors is closer to the goal, and use that to guide your main search algorithm. Our domain specific heuristic functions that we said, they were static functions, they had constant time complexity. Domain independent heuristic functions typically have polynomial time complexity. So, we will not look at these other algorithms, we will only have a quick look at this algorithm Graphplan, because it presents us with a new way of solving the planning problem. So far what we have been doing is that we have been doing state space search. So, you have the start state on the left here. It has some propositions P1, P2, P3, P4. You can do action A1 or you can do action A2, and you will go to either state 1 or to state 2, and then of course, the algorithm has to search through these possible sequences of actions. What the planning graph does is that it merges the states together. So, you can do action A1 or action A2 as before, but you do not store those states independently. You collect together the propositions of their resulting states and do a union of them. So, in that sense they are merging essentially. So, it does not no longer represents a state, it represents a set of propositions which we call as a proposition layer essentially. So, this is the first step you do towards building a planning graph. So, this is what a planning graph looks like a little bit. The basic difference between state space for planning problem and corresponding planning graph is as shown here. The state space search generates a successor candidate state, that is important, which will be a starting point for further exploration if you are doing forward state space planning. The planning graph is a structure as shown here on the right, which merges the states produced by different actions that are possible in a given state. So, for the moment we will say a given state, but we will see that which are possible in a given layer. So, for example, this is the action layer. You can think of this as an action layer. All the actions that are possible in the action layer will result in a set of propositions whose union will give us the proposition layer. Initially, of course, there is only one, the proposition layer, which we will call as P0, has the initial start state. There are two actions which are possible, and that gives us the second state essentially, or second layer, which we will call as the proposition layer. So, this would be called as P1 for example. So, there is an action layer A1 which results in the proposition layer P1 and so on and so forth. We will see this in a moment. The resulting set of propositions form a layer which is different from a state, which means that they may not necessarily be physically possible essentially, and as does the set of actions that resulted in this layer as we saw. The planning graph is thus a layered graph made up of such alternating sets of action layers and proposition layers. So, let us look at that. This was the state space approach that you in this problem that we are looking at. So, we are not at this moment concerned about what the goal state is. We just know that this is the start state here, and the first node on the left shows the start state. Then you can see that there are two actions possible, pick up C or unstack A from B. They take you to two different states, state 1 and state 2. In the planning graph, we merge them essentially. So, as I said, this is the proposition layer 0, which is equal to the start state. Then this is action layer 1, and then this is proposition layer 1. So, we put all the actions into one layer and all the resulting propositions into another layer. So, you can see that for example, on table is here in the state and it is here in this state, clear C is here, clear C is here, hold C is here, hold C, which is short form for holding C, on AB is here, on AB is here, clear A is here and clear A is there. And you can see that even the propositions from this also find their place in P1 essentially. So, it is a union of all things essentially. You can see that some of them are repeated here, on table, clear C, but this is new and so on essentially. So, this gives us an idea of how to construct these layers. You take all applicable actions and then collect together the effects of those actions. Now, there is a particular action which is called a no-op action. A no-op action basically does nothing, and it is applicable for any predicate. So, a no-op action is always applicable, and for each predicate that we have in the predicate layer, you can have a no-op action, and what it does is that it produces the same predicate essentially. So, if you look at on table B, then the no op produces on table B. It has one precondition, which whatever is the predicate you are looking at, and one positive effect, which is the same predicate essentially. It basically does not do anything. Thus, you can see that every proposition in any layer will be replicated in the next layer essentially. Why? Because you always have no op actions which are applicable. So, they will always be applicable. So, whatever the start state was there in P 0, that will be there in P 1 also, and that will be there in P 2 also. Of course, in addition, there may be other actions which are applicable that I have not shown in this diagram. In this diagram, I have only shown the no op actions. So, at least these propositions will get carried forward essentially. So, we will assume that no op actions are always present, and to avoid cluttering up our diagrams, we will not draw the no op operations essentially. We will assume that they are there essentially, which means that whatever is propositions are there in any layer, they will also get copied into the next layer, because no op options would do that essentially. So, the action layer contains set of all individually applicable actions. Okay. So, this is what we had to begin with. You had P 0, which is the start state, which is shown on the right. Then we had P 1, which contains, which is same as P 0 to start with, at least because of the no op operations, which we are not showing. So, all of those whatever predicates were there in the start state will also be present in P 1 because of no op operations, but there would be more. So, we have seen that there are two operations which were applicable in the start state. One was pick up C and the other was unstack A from B. So, they will come into the first action layer apart from the no op operations, and they will have connections to the preceding layer and the succeeding layer. What are the connections to the preceding layer? We have these precondition links. What are the preconditions for pick up C? C should be clear, C should be on the table, and arm must be empty, and likewise for the other actions. So, we have this set of precondition links. Then we have the positive effects of these actions. What is the positive effect of pick up C? Is that you are holding C, and what is the positive effect of unstack A from B? Is that you are holding A and B has become clear essentially. And then finally, we have the so the positive effects are shown by effects positive links here, as shown here, which are shown in these black lines here. Finally, we have the negative effect links, which say that these predicates are being deleted. So, for example, if you pick up C, then you are going to delete on table C. That is shown as this negative link here, which I have drawn in red arrows here, ending in a circle. So, for every action, there are three sets of edges, three kinds of edges. One is a set of precondition links which take them to the preceding proposition layer, and then there are the positive and the negative effect links which take them to the connect them to the next proposition layer. Even though we have these delete effects, for example, when you pick up C, you are going to delete on table C. On table C will be present in the next proposition layer, and the reason for that is, as we have already discussed, that no op operations are present all the time, which we have not shown here, but for every such every proposition on the left, there is a no op operation on the right, and that is why we got these initial which is the same as the initial state into proposition layer P 1 also. So, even though some of them are being deleted, for example, whether you pick up C or whether you unstack A from B, arm empty is definitely going to be deleted, but it is present in this layer because of the no op operation, but it is said that this is a delete effect of both these actions, but it is present in the layer, that is the important thing. Because of no op action, the actions and propositions in the I minus first layer, they will get replicated into the next layer. So, because whatever actions were applicable in the initial layer or the start layer will be application also in P1, because they all those things have got copied here, and then they will be again applicable in P2 and so on and so forth. So, they will keep getting replicated there. Of course, there will be newer actions. For example, in the starts layer we had pick up C and unstack A from B, which resulted in those new predicates holding C, holding A, clear B, and this may result in newer actions which I have not shown here, but what I am talking about here is the fact that because of no op operations, any action which is there in layer AI will be present in layer AI plus 1, and any proposition which is present in any layer Pi will be also present in layer Pi plus 1 essentially. In practice, of course, apart from the carry forwards from no ops, there would be other actions also, new applications and their effects also have to be incorporated. So, in this example you can see that there are in action level 2, in action layer 2A2, there are all these actions possible, because you are holding C, you can put it down or you can stack it onto A, or you can stack it onto B, and likewise because you are holding A, you can do the same thing with A, you can put it down or stack it onto something, because of which new propositions get added to the proposition layer. So, you can see that the proposition layer will grow and the action layer will also grow. We have not drawn all the effect links because that would clutter up the diagram. So, the important thing to observe is that the action layers and the proposition layers, they grow monotonically as the planning graph is grown. How is it grown? You start with P0, then you fill up A1, then you fill up P1, then you fill up A2, then you fill up P2, and the elements in all these layers, they grow monotonically. But there are other links that we are interested in, and these are called mutual exclusion links, and we use the term Mutex for that. Mutex stands for mutual exclusion. So, two actions in some layer, let us say the ith layer, and the actions are A and B, are said to be mutex if one of the following conditions hold. Remember that these two actions are in the same layer. Mutex links are always within one layer. So, they are in some layer I, and these are actions A and B. They are mutex, and by mutex we mean that they are mutually exclusive, that both of them cannot happen in parallel together essentially. Only one of them can happen, and that is what we mean by mutual exclusion here. So, if they have competing needs, for example, there exists a proposition in the which is the precondition of A, and there is another proposition PB which is the precondition of B, such that the two propositions PA and PB are mutex. We will define what it means for propositions to be mutex. So, basically they cannot happen at the same time. So, an example of two propositions which are mutex is holding C and on table C, both cannot be true at the same time. So, if there are some such if actions A depends on holding C and action B depends on table C, then clearly action A and action B cannot happen at the same time. So, they will also be mutex. So, the first condition for mutex is that they have competing needs, they have propositions which are mutex as preconditions. Then they have inconsistent effects. A and B can have inconsistent effects. There exists a proposition P such that P is a positive effect of A and it is a negative effect of P. So, one action is adding A, the other action is deleting, one action is deleting P and the other action is adding P. The action A is adding P, as you can see, it is in the P is in the positive effects of A and P is in the negative effects of B. The semantics of these actions in parallel cannot be defined. You cannot say what will happen if both these actions are happening in parallel, and therefore, we say that they are mutex. If they are linearized, that A happens first and then B happens, or B happens first and then A happens, then their effect will depend upon the order. Then we talk about interference. There exists a proposition P such that it is a precondition of A and it is a negative effect of B. If P is a precondition of A and P is deleted by B, which means it is a negative effect of B, then what is the meaning of saying that these two actions happen in parallel? Because there is only one linear ordering of the two which would be feasible, which would be that A should happen before B essentially if you are going to convert them. But we say that these actions cannot happen in parallel. And also the last condition is that there exists a proposition P such that it is a precondition of A and it is a negative effect of A and it is also a precondition of B and it is also a negative effect of B. So, basically both of them are going to consume the proposition P and delete it. So, both cannot do it at the same time. So, for example, arm empty, if your arm is empty, then you can pick up block A or you can pick up block B. It is a precondition for both pickup actions and it is a delete effect in both actions. Once you pick up A, arm empty would be deleted. If you pick up B also, arm empty would be deleted. And now we say that both cannot happen at the same time, so they are mutex. So, these are the 4 conditions under which actions are said to be mutex, which means that if you have a final plan, the final plan can have parallel actions as we will see as it happens in partial order planning, but it cannot have mutex actions in the same layer essentially. So, if you have a 2-armed robot that we talked about, you could do 2 pickup actions independently, but they would be different actions. So, one would be for arm 1 and the other would be for arm 2. So, here is an example of some mutex relations here. We have not drawn the complete graph, but in the initial state there are 2 actions possible, pick up C and unstack A from B, and we have shown one no op operation, which is that yellow action that we see. Now, you can see that pick up C and unstack C are mutex because of condition 4 essentially. What is condition 4? It says that they are consuming something, and the example I also gave was that of arm empty. Both need arm empty to be true and both are going to delete arm empty. So, only one of them can actually do it. So, obviously, we know that if with a one armed robot you can't pick up a block and so it should have been unstack A from B instead of unstack C. So, you can either unstack A from B or you can pick up C, but you can't do both the things together. At the same time, you can see that pick up C is also a mutex with this no op option essentially, and this is because of condition 2. What was condition 2? Condition 2 said that they had inconsistent effects. There is a proposition P such that P is a positive effect of A and P is a negative effect of B. So, for the case of this no op action, you can see that this no op action has a positive effect which is on table C, because it is a no op. On table C was true to start with and no op says that on table C will be true to end with. But pick up C says that on table C was true to start with, but it is deleted in the next layer. So, it is a negative effect essentially. So, that means that either the no op can happen or pick up C can happen, both cannot happen at the same time. So, pick up C is also mutex with this on table C no op on table C because of condition 2. On table C belongs to the effects, it is a negative effect of pick up C, or it is deleted by pick up C, and it is a positive effect of the no operation. So, this is just to illustrate the 2 mutex actions, but remember that the mutex links are only within a layer and we have shown them with dotted thick red lines here. Now, we are talking about propositions. The definition for propositions is simple. 2 propositions P and Q in some layer Pi are mutex if all combinations of producing them are mutex. All combinations of actions that can produce this thing, where action A produces P and action B produces Q, but if A and B are mutex, then P and Q cannot be produced at the same time. And so, if all combinations of actions which produce them together are mutex, then propositions P and Q cannot be true at the same time. So, we have mutex relations in action layers and we have mutex relations in proposition layers essentially. So, here are some mutex propositions you can see. You can either hold C or you can hold A, or you can either hold A or it can be on A can be on B, and so on and so forth. So, there would be many mutex relations in the proposition layer as well. So, now we can visualize the full planning graph. I think is made up of the following sets associated with each index I. So, for every I that you can think of, the following sets of relations or propositions or actions are there. The set of actions AI in the ith layer essentially. So, that is the action layer AI. The set of propositions Pi in the ith layer, the proposition layer which we call as Pi. Remember that AI produces Pi. So, A1 produces P1, A2 produces P2 and so on and so forth. P0 is the start state essentially. The set of positive effect links associated with the actions in the ith layer. So, every action in the ith layer will have positive links to the proposition which is also the ith layer. Remember, action layer AI produces proposition layer Pi. So, there are positive links between the two, and there are also negative links between the two as we have seen. Then there is a set of preconditions, this thing. So, for the ith layer of actions, the preconditions for these actions are there in the preceding layer of propositions. So, preconditions of action layer 1 are in proposition layer 0 and likewise for others. And then finally, we have the mutex layers, the set of mutex in the ith layer, which could be both for actions and for propositions. The set of action mutexes and the set of proposition mutex in the ith layer essentially. All these sets they together define the planning graph essentially. And the planning graph is gradually grown. So, initially we have only P0, then we add A1 and P1, then A2 and P2 and so on and so forth. So, till when do we do that? First observe that if two propositions are non-mutex in a layer, which means they can be true together, then they will be non-mutex in all subsequent layers because of the no-op actions essentially. Likewise, for two actions that are non-mutex, because for the same reason essentially. In P0, the start state, all propositions are non-mutex because P0 depicts the start state and it is something which exists, all the propositions can happen together. As the graph grows, more layers are being added, the number of propositions grows monotonically, the number of actions grows monotonically. We have seen that the number of mutexes first increases and then gradually they decrease. Okay. So, that can only be seen if you actually take up a small problem and try to construct a planning graph. You will see that certain propositions may be possible after 4 actions, but they may not be possible after 2 actions. So, it is after 2 actions they may be mutex, but after 4 actions they may not be mutex. So, for example, if you just take up 2 propositions like on table A and on table B, it is not possible that you can achieve them in one action, but in 2 different actions you could achieve it. So, they would be non-mutex at some later point because some sequence of actions, some combination of actions would allow them to be achieved, including actions which are non-OF essentially. So, for example, if A is on B and C is on D, then you can pick up A, you can unstack A and put it on the table, you can unstack C and put it on the table in the first 2 layers. In the first layer you unstack A or you unstack C. In the second layer you put it down on the table, but both A and B cannot be on the table, but you can imagine that A and C cannot be on the table, but you can imagine that after 4 layers or 4 actions, you can unstack A, put it on the table, unstack B, unstack C and putting it on the table, and both will become non-mutex in the fourth layer. So, mutexes first they increase and then they from 0 and then they decrease essentially. So, that is the observation that you should think about. We have already said that the planning graph grows monotonically. So, what does it have? It has these yellow links which are no ops. It has these black links, black edges which are either preconditions or positive effects. It has these red edges going from one layer to the next which are negative effects, and it has these thick red edges within layers which is the mutex actions, and the planning graph grows monotonically. So, the process of extending the planning graph continues till any one of the following conditions is achieved. So, you keep growing layer 1, layer 2, layer 3, layer 4. If the newest proposition layer contains all the goal propositions that you are interested in, and there is no mutex relation between any of these goal propositions. If you reach such a layer, then at least potentially you have a plan which will achieve those layers essentially. And then the second stage begins, which is to start seeing if a plan is possible. We will come to that in a moment. The other condition when you stop growing the planning graph is if it is what they say as leveled off essentially, which means no further changes are likely to happen in the planning graph. This means that for 2 consecutive layers, the proposition layers do not change and also the mutex layers do not change essentially. So, remember that proposition layers anyway were either growing or they can be stagnant. Mutex layers we said will increase initially and will decrease later. But if in 2 consecutive layers nothing is changed, then that essentially means that no further change can happen and you can stop growing the planning graph, and if there is no solution, then there is no solution. Okay. So, that is what I have said here. If 2 consecutive layers have the same set of propositions with the same set of mutual relations between them, it means that no new actions can make an appearance after that, and hence if the goal propositions are not present in the leveled planning graph, they can never appear and the problem has no solution. So, in either case it will stop growing the planning graph. In the first case, if you find that the goal propositions are present and they are not mutex, then you will search for a plan and the search will happen in the backward fashion. If you find a plan, then you report the plan. If you do not find the plan, you come back and grow the planning graph by one more layer and try again. So, a consequence of this, if you think about this, will be that the first time when all goal propositions are present and a plan is found, it will also be the plan which has the lowest make span or the lowest time steps needed, because you keep growing the planning graph and keep testing whether there is a plan or not essentially. Incidentally, the same approach is also tried in SAT plan. They keep exploring longer and longer plans to see if there is a valid plan essentially. So, there is some similarity between these 2 algorithms. So, let us imagine that this is the case here, that P7 is one of the goal propositions, P4 is one of the goal propositions and P5 is one of the goal propositions. So, let us say there were 3 goal propositions G1, G2, G3, and they can be identified as P4, P5, P7 essentially. Then we start searching backwards. What does it mean? This is like doing backward state space planning, but within the planning graph essentially. Is what can be the sub goals for achieving P7? So, the action that achieves P7 is the one which is shown in thick black lines, and the preconditions of that would be the propositions that should be present in the previous layer, this thing, if that was to be part of a plan. And likewise, as you can see for the other 2 goal conditions G1 and G2 or P4 and P5, these are the preconditions. So, if these 5 elements P1, P2, P3, P4, P6 P2 is this one, P5 is missing from here, as you can see, and it is missing from here. So, if these other things are present non-mutex in the preceding layer, then we can continue searching backwards from there. So, that is one possibility, that the sub goal set, if you can think of this as a sub goal set. What is the goal set? G1, G2, G3. The sub goal set is P1, P2, P3, P4, P6 essentially. Some of them are the same as G1. So, for example, P4 is same as G1, as you can see. That is one possibility. Another possibility could be that just P4, P5, P6 are enough to produce those goals, the same goals G1, G2, G3 we said. So, there are different possibilities. So, this brings in the fact that you can do search, you can try this sub goal set or you can try another sub goal set. What would happen from there? Then you would look at the preceding layer from here and see that are there some sub goals here that can be achieved, and then eventually can they reach some sub goals in the start state, essentially a little bit like backward state space planning. But at every stage they must be non-mutex, that is the condition. This is what I have said here, that they must exist non-mutex essentially, which means they can happen in parallel together. So, when the goals are found non-mutex, is found, then it is possible, but it is not necessary that a valid plan might exist in the graph. The algorithm regresses to the set of sub goals that is also non-mutex. So, you regress to, remember regress is a little bit like backward state space planning, and it continues this process in a depth first fashion. It keeps diving down or diving back towards the start P0 layer. If it reaches P0 layer and there are no mutexes which show up on the way, then you have a solution. All the actions that you are there in this backward search, they will be part of the plan. They may be parallel actions. So, some layer may have more than one action, which means that they can in principle be done in parallel. But it will be the shortest plan because of the fact that we keep growing the planning graph. As soon as the goals appear non-mutex, you start searching backwards essentially. If you find the plan, then it must be the shortest plan or the plan with the lowest make span. If it cannot find a sub goal set at some level searching backwards, it backtracks and tries another sub goal set. So, we saw an example of two possible sub goal sets. So, it will do that first search, it will go off in one direction. If it does not succeed, it will come back and try another direction. If it reaches the layer P0 at some point, it returns the subgraph that is the shortest make span plan. What is this subgraph? It contains all the actions which are there in the plan that you have found and all the propositions which are there on the way. And as I said, those actions may be more than one action in a layer, which means that they can be done in parallel essentially. Else, if it cannot do that, it extends the planning graph by one more level, and then this is process. So, remember that if the goal set in our example G1, G2, G3 appeared non-mutex in some layer I, it will also be non-mutex in some other layer this thing. And so, you will go to the next layer and again search for a plan, then you will go to the next layer and again search for a plan. In the process, you will end up finding the shortest plan. If while creating the next layer, we reach this other condition that it has leveled off, and we said that when does it level off? When two layers have the same propositions and the same mutex relation. If that condition is reached, that you can not add any more propositions and any more and the mutexes are not declining, then you can report failure, which can be like a nix. So, this is what it does, that it extends the planning graph by one more level and searching for the plan, and it will only stop when the graph has leveled off, which is the condition that we had spoken about here, that the two layers have become static essentially. So, we can think of the backward phase or the second stage of the planning as doing depth first search, and this tree that you see in thick lines is the tree that it explores. Now, subsequent to Graphplan, there were other approaches which said that okay, you construct the planning graph, but how do you solve that? Instead of doing depth first search, maybe you can do constraint satisfaction, or maybe you can even do pose it as a SAT problem. So, various lines of research came forward, but we will leave planning at this stage and move on to our next topic, which is going to be and or trees essentially, or and or graphs.